The starting point, I guess, of thinking of R is it can be a little bit like a calculator at the most basic level. You know, you can do basic addition, subtraction, and so on. I'll just mention briefly, instead of clicking run to run commands, I will be using the keyboard shortcuts. So basically, you can just press Control Enter if you're on Windows, or Command Enter, and that will run the current line. So that's usually much simpler. So I'll just be pressing Command Enter, and then that runs the current command and sends it to the console. So as I say, you can do basic addition, subtraction, multiplication, division, and all that sort of thing. R also has the standard mathematical functions like getting the absolute value. So here's our first example of a function, which is called ABS for absolute, and you can pass it a value and it will return the absolute value. Or things like getting the rounded up value or the rounded down value, square roots, exponents. It also has the mathematical constant pi. It's just literally the word pi, or at least a numerical representation of it. And it's got all the standard other mathematical functions you'd expect, like exponentials and logs. If you want to control order of operations, you can use parentheses. So that's obviously two different things. It also has a range of logical operations. So often you want to be filtering data and saying, if this is true, get the male. So if gender equals male, then return true and so on. So the language definition of true and false is capital TRUE and capital FALSE. If you want to sort of be cheeky, you can do capital T, that's also true, and capital F, that's also false. But most language guides would tell you to write it out in full. You can test for equality and inequality. Equality is double equals, not single equals. Not equals is the bang equals, and greater than, less than, and so on is fairly straightforward. True and false converts to 1 and 0 if you're doing things in a numeric way. So that's a function that converts a true-false to a number, and true converts to 1, false converts to 0. Just to highlight why, and this is sort of an aside, but why that is useful, if we had a vector of numbers, so we had a bunch of numbers stored in X, called the numbers 2, 5, 7, 10, and 15. If that was our data, I don't know, number of people that had attended an event over 5 days, we could see which of these values are greater than 5. And sure enough, the number position 3, 4, and 5 are greater than 5. It's quite nice that it converts to true converts to 1, because then we can see that the sum of that that vector of false and trues is 3. So 3 people had a value greater than 5. Or the mean of that is 0.6, so that's a proportion. That just gives you a feel for some of how true-false works in this code. All right, probably the next most important thing is the concept of assignment. In most other languages, you would assign a value to a variable, something like this, x equals 1 plus 1. And that would mean that x equals 2. I don't know. So who here has done any, does any programming whatsoever, ever? A few people. Yeah. So if you've ever done any programming in any language, just about every language would use the equal sign to assign values from the right to the left. R is different, which is irritating, but that's the way it is. Well, actually, you can use equals if you really want to. You can as an assignment operator if you find it more intuitive. But the R way of doing things is to use less than minus. That is the what they call the assignment operator. I think the idea is that it more clearly represents the idea that you're sending the stuff on the right, 1 plus 1 for example, you're assigning that to the value x. So you're not saying x equals 1 plus 1, you're saying assign the value 1 plus 1 to x, which that's what you do. Yeah. But if you really like equals as an assignment operator, it does work. All right. And a little commentary now about variable names. So you're always creating variables. Variables to represent data sets, variables to represent names of variables in data sets. You would use a variable to store the results of a regression model. You might use a variable to store a plot. The general rules with variable names is that they need to start with a letter. Then they can be followed by any number of letters, numbers, underscores, or periods. You can't have spaces in variable names. So if I tried to assign 1, 2, 3, 4, like a number, to a variable name called my space variable, it's saying that doesn't make sense. If I try to do it, starts with a number, that doesn't make sense. Yeah. So what is allowed is variable names like this. So my variable, all one word, my variable underscore, letters and numbers, letters, dots and numbers, and so on. They're all legitimate. I guess in general you want to come up with a naming convention that is both descriptive but not too long. So it's easy to type and easy to read. So I quite like short descriptive names, maybe 8 characters. And that's not a strict limit, it's just sort of a readability guideline. I quite like using underscores to separate words, and I quite like using all lowercase letters. That way I don't have to think whether anything is lower or uppercase. Yes. You can also have names that start with a period, and they'll be hidden when you want to look for them, which probably isn't that useful, I guess, but occasionally it might be. If you want to see the variables in your workspace that you've created, you can use this ls or list function. And you can see these are the variables that I've created so far. And then you could then look them up by typing them. Alternatively, we have what's called the environment pane. So that also essentially lists what we saw before using the ls function. So that's a nice feature of RStudio. You can keep track of what variables you've created here. Throughout this script, you'll see these hashes. That's the comment character. So if you want to comment your script, and generally it's a good idea to sort of leave mental notes for yourself, you can start a line with a hash, and that whole line will be a comment. Or if you can add it to the end of a command, and that will be everything after the hash will be a comment. So you can sort of have parenthetical comments at the end of a line, or whole sort of big chunks of comments before. In general, R is quite tolerant of spaces between what we might call syntactical units. So you can't have spaces within variable names. That's not allowed. But you can have either no spaces or many spaces between variable names, operators, function names, elements, and so on. So here's an example of no spaces, and sure enough, that worked. Here's an example of a ridiculous number of spaces, and sure enough, that worked. But probably as a rule or as a convention that is readable, you generally put spaces between operators, spaces after comments, commas, and so on. So it might look a bit like this. That's kind of, and I'll try and use that sort of good R writing style throughout the day. You can also span multiple lines as long as R doesn't think that the command has ended. So this works because there's nothing about this first command that R thinks that the command is ended. So you can just keep going. This works because we have a plus operation here, so R is expecting something after the plus. So that did work. Whereas this doesn't work because I've put the plus on the next line. So essentially, if I run that, it thinks the command's over. I've assigned the value 10 to Y. So yeah, you can span multiple lines, but you just have to make sure that R doesn't think that the command's over. You can even include multiple commands on one line, but it's generally not a nice thing to do. It generally reduces readability. The semicolon is the way to separate multiple commands on one line. So this would assign values to X, Y, and Z, and then I can print them all in one go. One thing that can surprise people coming from other languages, particularly Windows, I think, is that R is case sensitive. So that the variable lowercase test is different to the variable uppercase test. So that can be the source of some confusion. That's why I tend to, whenever I create variable names, just stick to lowercase. That way I don't have to think, is it lower or uppercase? Even mixed case is possible. So that can be, if a function is a mix of lower and uppercase and you've typed it in the wrong case, that can be sometimes a source of errors. Another thing that can be challenging for beginners is the concept of a working directory. If you've ever used anything from the command line, you'll be familiar with the concept of the working directory. So if you've ever opened up something like a terminal or a command prompt, you'll be familiar with the working directory. But if not, this may be a new concept. In general, your projects in R will revolve around a particular folder. And everything within that project is related to that project. And so your working directory will generally be that folder. We can see what our working directory is by typing the get WD, get working directory function. And we see that I'm in my user directory, users Jeremy, and then I'm doing some other stuff, there's teachers, our training materials, and I'm in the training exercises working directory. This is also reiterated in the very top bar of the RStudio window. So this becomes important whenever you're trying to access files like data on your computer, or you're trying to write files to your computer. In general, they will all be relative to your working directory. So if you store your data in your working directory, it's easy to refer to that file because you can just say, oh, it's this file in this working directory, rather than having to write out the full path to the file. Now, one of the beginner mistakes is people start RStudio up, and by default, you will end up in your home directory. So something like users Jeremy. And you get into all sorts of trouble because you can't find files or you can't load files. A general tip is there's various options. Probably the general tip is to use what are called R projects for your analyses. So we saw at the beginning that we opened this introduction to R workshop.R project. And that's how we opened RStudio in a sense. And by clicking on that R project file, it ensured that we opened in the right working directory. It retains that information. And you can create your own R projects by going to New Project and going through everything. Uh-oh. So, and you can access your recent projects like this. Okay, so an RMD file is just one of my script files in the project. So the project is the overarching concept of, it should be, you have the RStudio project file, which stores general project information. And then in a typical project, you would have script files, data files, possibly stuff that you've generated, table output or plots that you've saved, maybe configuration data and all sorts of things. If you ever find that you're in the wrong working directory, you can set the working directory in R using session set working directory. And you can set it to the project directory or the particular file you're in and so on. Yes. You'll also notice that we are in an R, what is called an R session. So generally when you start R, you will start a new session and the workspace will be empty and so on. If you find that everything's gone a bit haywire and you want to start a new session, you can go to the session menu and restart the session. Okay. In general, I think also it's worth saying a little bit about file names. So because you are working in folders, and generally you'll have multiple files for scripts and data, there's a few general tips in terms of how you name your files and your folders. Probably the big one, if you've come from Windows, where spaces are perfectly reasonable in file names, I would generally avoid spaces in file names. So notice how all my files are called like 1-core-language and so on. There are ways of dealing with spaces. You kind of have to use this escape character, so you have to, General tip is try and avoid spaces in file names, and you're less likely to run into issues. If you are on Windows and you've got a basic machine, it may be hiding file extensions. I would generally disable that option. You want to see file extensions. You want to see the .pdf, the .rmd, the .rproj. That's quite often useful information when you're working with R, to know what type of file it is. You don't want just Windows hiding that information from you. And the general idea is that while maybe working with other statistical programs, you can kind of have your files all over in different spots in your computer. In R, the idea is you have a project folder, and everything related to that project is stored within that folder. So we'll go into ways of organizing things, but you can see here, I have the training exercises folder. I have a number of script files that I'll be working through today, like there'll be the graphics and data manipulation, statistical models. And there's a bunch of other things where we'll store data in a data folder and write output to an output folder and so on. So just general idea is to be organized with your files and folders. Okay, so now let's talk about R sessions. I said you could, R automatically starts a session when you load RStudio, but you can restart an session if you want to kind of refresh the environment, get rid of all your variables. In general, in our studio, if you quit RStudio, you quit R, so that's fairly straightforward. But there is a function, the Q function, which, well, there you go, allows you to quit R. Where are we? Okay. When you're working with R, you have what's called a workspace, which stores the variables that you are working with. So R is kind of organized, the workspace is organized hierarchically. So the first level of the hierarchy is what's called the global environment. And that's kind of what you'll generally see in this pane here. So if you create a variable like X, it will be listed in the global environment. And that's what, when you type in list, it will generally show what's in the global environment. After that, you have a number of attached packages, which we'll go into later. But the idea is that when you type a variable like X, it will first look for it in the global environment, and then we'll look for a function or something in any of these attached packages called X, and until it finds something that matches, or if it doesn't match anything, it'll return an error. So yeah, as I say, we can create variables or even attach data from built-in sources, and that will all show in the workspace. Yeah, well, as I say, the simpler option is just to look at the global environment and you'll see a list of these objects that you've got. You can also remove objects from the workspace if you're sort of sick of it being there or if it's interfering with anything, with the RM function. So that's RM for remove. So now we can see that X is gone. You can also remove multiple things or even send it a list of all the objects in the workspace with list equals ls argument. Alternatively, if you want to just remove everything from the workspace, you can use this little broom icon that sweeps, so to speak, all the objects in the R workspace away. Yeah.
The list of packages.
Yep.
That's the ones, like when you did search, that's just the ones that are currently loaded, like you've got a whole lot that you've installed. Is that different?
Yes. So I'll go into that I'll go into packages in a little bit, but yeah, the general idea is that if you want to use a package, you need to install it once, and then you've got it on your computer, just like you would install any software. But if you want to then use it in a particular session, you would have to load it. And there's a function called library to do that loading, and you would do that each time. For each project, you would have a bunch of little library commands at the top that would load that package that you want to use for that particular session. Yeah, I'll go into that in a little bit.
Sorry, what's the difference between a global environment and global workspace? Is that the same thing?
Yeah, so what's the difference in global environment and a global workspace? It's probably just my sloppy terminology. The workspace is probably everything, and the workspace is composed of environments, and the main environment that is the global environment, where you store your objects that you're working on at the time.
I have workspace but not environment. Is that a different version of IBM?
Do they call this workspace? Oh, that's interesting. Yeah, don't know. I wouldn't worry about it. Yeah, RStudio is constantly evolving. It's bringing out new features all the time, and there are slightly different versions. I can't resist but install the latest, slightly flaky, but one with the latest cutting edge features that's about 2 months ahead of the normal version, just because it's nice to see the extra features. But yeah, so there might be slight differences. If you want to save everything in your workspace to a file, you can use this save.image. And that will create this .rdata object, which could then be loaded in at a later date. So it's just storing all the objects that you've created in R. You can also save particular objects to a file. So I will save X and Y to a file called y.rdata. So I put that in the output folder just to keep it nice and neat. And sure enough, in here somewhere is y.rdata. So if I were to remove X and change Y and then load that data, we would see that X and Y is back to normal. In general, I discourage people from using save.image and instead encourage you to try and learn reproducible workflows, which we'll get into later in the day, where essentially you have a script that loads your data, sets up your libraries, and does any initial data manipulation. So there'll be one command that sort of gets you into wherever you want to be to get started for the day, rather than working for a while, saving your image, going away, coming back, loading your image and returning. That's okay, but best practice is to try and set up some sort of script that you run once and it gets you up and running to where you want to be. So we'll talk about those kind of scripts later in the day. R is composed of what are called data types. So you have things like logical variables, character variables, and numeric. They're probably the major types you'll encounter, where numeric is sort of composed of integers, i.e. numbers without decimal points, and numbers with decimal points, i.e. real, or what are called doubles in computer terminology. So we can create vectors of these kind of types using this C function. So that would create a vector of true, false. We can create character vectors or variables with quotation marks around either single or double. We can create integers and doubles. If you want to know, what type of object it is, you can use the is functions. So is it logical? Yes. Is it numeric? Well, this is character, so no, it's not numeric. Is this character? No, it's not. It's numeric. R generally is, I think they call it a loosely typed language. It will generally convert arguments for you as needed. So it will convert strings into numbers if a function expects numbers and so on. You can also deliberately convert things from one type to another. So you can make numbers into strings with as character. You can try and coerce strings into numbers if it makes sense. And you can convert logical to numbers. So as I say, it will often do implicit conversion when you run a function, like the sum function will convert logicals into 0, 1s. The paste function pastes, say, the letter V, and these numbers, it will convert these numbers to letters before it applies the paste. R is also composed of several sort of basic data structures. So these include vectors, lists, matrices, and data frames. So we can assign a value to, with a single value, what we might call a scalar, like just a single number, but that's essentially a vector of length 1. We can create vectors using the C function, which stands for combined, and now we've created a vector with 4 values, 1, 2, 3, 4. There's also ways of creating sequences with the colon or with the sequence, so 1 to 10, or 1 to 10 by 2, or repeat the number 1 5 times, or repeat the numbers 1, 2, 3 5 times. R also has a lot of functions for simulation, which we'll get into later. So we could sample some values a bunch of times, or we could use some simulation function to create some normal random variables with particular distributions. If you want to extract values from vectors, you can do it by position, or use a true-false sort of operation, so get the values that are less than 3, or as named arguments. I'll just have to give them names. You can create matrices, but generally you'll derive these from, say, a correlation matrix or some data source. So you can get the dimensions of your matrices, either rows and columns. You can give names to the rows and columns. You can extract elements from a matrix by name or by position, and so on. Generally, matrices aren't what you would use to store your like normal kind of data sets. They're usually used for specific mathematical things like correlation matrices, covariance matrices, distance matrices, things like that. Lists are a very flexible data structure. They're often used for storing the results of a statistical analysis. They can store a mixture of types, and they can even store lists themselves. So this one stores a mixture of strings, numbers, logical, and then a list itself. A nice feature of lists is there's quite a bit of code completion. So I have a list called W, and if I type $, you should pop up the elements of the list. So W, $, caret, there it is. If you're not getting automatic code completion, then you may have to hit Tab. There are a bunch of options for code completion under Preferences, and that can make coding a lot more easy in R. So you can use the $ notation to extract a particular element of a list, or extract a particular numbered element, or by name. You can extract subsets by number, by name as well. Just to highlight how lists might be useful, I'll just run a quick t-test comparing two group means. So that's kind of the output. T-test, not quite significant, whatever. We've saved the results of this t-test as a fit object, and we can see the structure of this list object using the structure. So it says it's a list of 9 elements, which includes a statistic, a parameter, a p-value, a confidence interval, some estimates, and so on. So we could look at the elements of this statistical analysis and see the t-value, the p-value, and so on. In general, there will be a more convenient sort of print function that will give you the main results. But if you wanted to kind of combine this into a table, you could extract each element and use that for your purposes. Data frames are probably the most important data structure in R for analyzing things. If you've analyzed data in SPSS, Stata, SAS, whatever, and you think of that row and column thing you have, that is your data, that's a data frame in R. So it can include variables of different types, and it's just a rectangular data structure, just like you would have in any other language. So if I create a data frame called Z, we can see it's got some numbers and letters. We can view this data frame by clicking on this little spreadsheet icon. And sure enough, there it is. It's got 2 variables, variable 1 and variable 2. You can filter that in various ways. But more commonly in R, you'd apply various arguments for extracting things. So let's have a look at a particular data set called the survey data set. It's a built-in data set. And it has just a bunch of questions that were asked to some undergraduate students. So I can extract elements by number in the rows, or reorder the rows by number. You can extract particular rows. The general idea is you've got rows, comma, columns. So if I want to extract rows, I could send it this argument saying, look, I want the people who are female, and so I could get the sex that equals female, and that would be a logical vector, and I could put that as an argument in the row. So, or I could do it by the names of the row. You can select variable names by number if you want, but generally you do it by name. So if I wanted to get the the gender and how they fold their hands information, I could put those two variables in a vector like that. So that's after the comma. And the autocomplete on variable names is very helpful, I think, with the dollar in RStudio. You can get the names of variables with the names function. You can also use that to rename variables. While you can look at data using this viewer, quite often you'll use things like the head function to show the first few rows, or 10 rows, or the last few rows. Yeah. And you can get the dimensions, rows, and columns, and so on. You can also see the overview of the variables with the structure command. If you want to get help in RStudio and R, there's a number of options. The first, so the first option is to put a question mark next to the function name, and that will bring up the help file in the help viewer. So if you know the name of the function, you can do that, and then you'll get some information about it here, which eventually lists the function name, basically what it does, the kind of arguments it takes, and the values it returns. And you also have some examples. You can get help on a particular package with help package equals the name of the package, and that will list all the functions in that package. And more generally, you can click F1 on a particular function, and that will also bring up the help. More generally, you can Google questions and search on Stack Overflow. Anyway, I think now it's probably time to give a bit of an exercise, and hopefully also we can resolve any installation issues. So yeah, there's an exercise here, which we might spend 10 minutes on. It just looks at creating some variables and using some existing data sets. And yeah, if you've got questions about installation or any questions about the exercise, put up your hand, and Sarah will also be roving the room to help out. Yeah, so give that a go for about 10 minutes or so.